stored. It's stored in the sequence of the RNA molecule, the messenger RNA, which can trace its lineage back to the gene in the DNA. And it literally moves past the ribosome. And the ribosome is the machinery that does the linking. So there'll be several of these codons, these groups of 3, exposed on the ribosome at the active site of it. There'll be a docking spot where it's waiting for the next guy to come in. In this case, it's glycine attached to its glycine tRNA will come in. And there will be molecular recognition based on hydrogen bonding. We'll expect AT or AU, because U is used in the place of T and RNA. AU-GC pairs will form that will allow this guy to recognize each other. The codon for the glycine tRNA will make a perfect match right there. And that will end up with a glycine amino acid docked right next to this growing chain. And then there's enzymes built into the ribosome that will actually create a peptide bond between that alanine and this glycine. And then it will slide down to the next codon. So one will get ejected, a new open spot will appear, the next tRNA will come in. And it's just moving down the tape, reading the next bit of information. So here's 2 tRNAs with their things attached. This was a tyrosine, so that's a tRNA specific for tyrosine. And how do we know it's specific for tyrosine? It's that tyrosine attached covalently on one side. If you look at the other side of the molecule, it's got the so-called anticodon sequence. This is made out of RNA, so this RNA molecule looks at the messenger RNA and it sees and recognizes that specific side. So there's molecular recognition going on there. That docks firmly in place, then the ribosome gets busy transferring this up to there. So there's an exit site, it's empty here, and a site where things come in, and a site where the growing chain sits. This is what the tRNA looks like. It's often shown as this famous cloverleaf pattern that's showing some of the secondary structure. The hydrogen bond pattern makes these little loops like a cloverleaf. Here's its 5' end, and you can trace it around here to its 3' end. It's at the 3' end that you actually attach the amino acid. We'll see in the next slide. I think that the amino acid is covalently bound to the sugar up there on that 3' end. And down here in the middle, this is the anticodon loop. This is the part that will recognize and bind to the messenger RNA at the ribosome. So that's its secondary structure. This is its higher level structure, tertiary structure. It kind of folds up into something that looks more like an electric drill or hair dryer or something. So up there on the 3' end, here's the last amino acid, the last nucleotide in the tRNA. It's got its sugar attached, and at the 3' position, you have a covalent bond formed to an amino acid. So that amino acid is holding on really solidly to that tRNA until it's delivered to the ribosome. And this just shows kind of the steps in the building of that. Here you have the tRNA with, in this case, 1, 2, 3, 4 amino acid chain. It's bringing in the 5th guy. It knows which one to add based on the codon here interacting with the anticodon there. To dock that incoming tRNA takes energy. And this is where I said you can use GTP. It takes 2 GTPs to get the correct alignment and strong docking. Then you transfer the growing chain onto the new guy that just arrived. So it gets longer by 1. This tRNA is now empty. You spend another GTP to move the ribosome down the chain, the next codon, kick out that last unused, used tRNA that doesn't have the amino acid on it. And it just goes through the cycle, using GTP here and here as the energy source.
Well, I'm sorry, the second, that kicks off
This
What
moves
does
it
that
down,
moves
yeah,
the chain down. And
moves the
that-
chain down, and as that happens, it falls off.